In this final lecture for Unit 12, we'll be talking about some of the ways in which we test the theories of the Big Bang. We've already touched on some of those tests, especially in the first mini-lecture, but here I want to go into more detail on those and other tests that have been done. A lot of people think that it's not possible to test what happened in the Big Bang because it happened 13.7 billion years ago, and we have no possible way of getting in a spaceship and traveling there. But the fact is we can test it. The Big Bang theory predicts that conditions in the early universe are similar to those that we can create in particle colliders like the Large Hadron Collider. We can test the physics of those times to make sure we understand our calculations and that they're producing believable results using particle colliders. Nuclear fusion, which happened between 100 seconds and 20 minutes after the Big Bang, first of all, it's tested by every star that we see. It's tested whenever we blow up a hydrogen bomb, which thankfully is very rarely. More important, the exact abundances, the percentages of each element, can be tested by looking at the purest gas that we can find in space, which is gas that's located in between galaxies. And when we measure abundances in that, we recover the predictions from Big Bang nucleosynthesis. We talked about the deviations in the temperature in the cosmic microwave background, those hot spots and cold spots, the number of those deviations, the sizes of those deviations, and the amplitude, the total temperature difference of those deviations, are predicted by the theories. Usually we calculate them by computer, and astronomers test those against actual observations of the cosmic microwave background. And finally, the growth of galaxies due to gravity and dark matter over time is modeled on computers, and those can be tested by real observations. So let's step through some of these tests. I can't possibly go through all of them, but suffice to say that all solid observational evidence points to the idea that our current Big Bang theory is correct. As I said on the previous slide, the conditions in the early Big Bang were similar to those that we can reproduce in particle colliders. And the Large Hadron Collider, which was built partially to detect the Higgs boson, which we now have found, it also has provided other hints as to what physics was like. And for example, we talked about how in the very early universe there were almost but not quite equal amounts of matter and antimatter. And some recent results from the Large Hadron Collider have shown that indeed if we produce conditions like those during the Big Bang, that we produce almost but not quite equal amounts of matter and antimatter. And this is a news headline from some of these recent results. We already saw this plot, which tests the cosmic microwave background. This plot was from an experiment called COBE, which looked at the entire sky in microwaves. And if you remember, we said that the curve is a prediction. The dots with the little error bars are the actual measurements, and they're not fit to each other. They just match up perfectly. This plot won a Nobel Prize for the team that designed the satellite that took these data. Here are the data themselves, because they're kind of fun to look at, and I said in the first mini lecture we'd look a little deeper. The actual data from COBE and from other satellites that look at the cosmic microwave background looks very close to the picture up top, which is basically that we see the same amount of noise coming from everywhere. So what we can do is we can just say, okay, if the universe were perfectly the same in every direction, we'll take that best fit temperature of 2.728 degrees above absolute zero and subtract it off. When we do that, we see the second map. And the second map shows that there's one part of the sky that seems to be hot and one side that seems to be cool. And what we're seeing here is a Doppler shift. The sun and our galaxy are moving through space, and this is the Doppler shift from that combined motion. And so in the direction we're moving, it's blue shifted. In the direction we're going away from, it's red shifted. And direction sideways to that, it's not shifted at all. So again, we can fit the Doppler shift and subtract that off, and when we do it, we get the map at the bottom. Now in this map, the big red bar across the center is the Milky Way, but we can actually measure the Milky Way at nearby wavelengths, take it out, and that mottled thing that's left behind, the bright and the dark spots, the hot and the cool spots, those are the echoes of the Big Bang. Temperature differences of 20 microkelvin or 20 10,000ths of a degree Kelvin. So very tiny fluctuations from the sound waves and the dark matter spots in the early universe. We can measure those spots, and this is a plot that shows on the y-axis it's how hot those spots are, and the x-axis is how big the spots are in actual size. And again, here the blue is a prediction and the red dots are the actual measurement, and these are from data that came from the Planck satellite, the most recent satellite to study the cosmic microwave background. And again, what you see is that the dots fit the predictions almost perfectly. At the big scales, we would expect the real universe to be somewhere along those red error bars, so we see that those points all match up. And then you get to the small scales, which are as you go to the right, and you see that things match perfectly. And so this is a very stringent test of the Big Bang, and these data also include in them, although it's not obvious from the plot, dark matter and dark energy, and those fit perfectly as well. So this is an extremely stringent test of not just the Big Bang, but the physics of the universe since then, and it matches exactly. And this is the sorts of things that gets geeky astronomers salivating. Hey, we know this stuff, we got this, we nailed it. So now we'll go to predictions of how gravity shapes the universe. And as I said back in Minilecture 2, after Big Bang nucleosynthesis, for several 100,000 years, gravity was the only force really acting on all the material, and it started to collect dark matter into small clumps. Then after the electrons and protons recombined and released the cosmic microwave background, then regular matter started to group together as well. And we can make computer models of that and compare it to what we actually see. So here's a short video showing some of these models. These are all computer models that you will be seeing, where we put in as much physics as we know and see what happens when you just let the universe go. So what we saw in that video is that the computer simulations show that the universe, even though it starts off extraordinarily smooth, it very quickly becomes filamentary, like a spider web. On the left is one of these computer models, not one that we saw, but a similar one. And you can see that by today, matter is clumped into what we call the cosmic web, where most material is either in a little filament or a junction of these filaments, and the rest of the universe is pretty empty, and we call those empty spaces voids. On the right is a slice of the real universe going out to a distance of roughly a couple billion light years. And what you see is that the real universe, qualitatively, meaning if you compare them, they look similar. You see those filaments, you see the little nets. There are statistical ways you can compare these, and what we find is that they are really close. They're not identical, but they're really close. And currently we're trying to understand if those differences between the predictions and the observations are pointing at some thing that we don't fully understand about dark matter, or something we don't fully understand about how galaxies form from clumps of dark matter, but they are extraordinarily close. I mean, strong evidence that our ideas of how the universe and structures in it grow over time is indeed true. So let's summarize what we've talked about in this mini lecture. The Big Bang Theory has been tested by several different methods, and it has passed all of these tests. We talked before about Big Bang Theory predicts expanding universe, which it is expanding. It predicts the amount of elements, which we find to be matched by our observations. It predicts the existence of a cosmic microwave background. And in this mini lecture, we saw that particle colliders can test the conditions that existed shortly after the Big Bang. What we see in those experiments at particle colliders matches what the theories tell us would have been happening in the Big Bang under the similar conditions. Measurements of the cosmic microwave background, not just the temperature, but also the small deviations from a perfect temperature, match the deviations that are predicted should be there due to gravity pulling on dark matter in the very early universe. And these computer simulations of gravity and the growth of structure in the universe, the growth of galaxies, come pretty close to matching exactly what we see in the real universe. All of this doesn't prove the Big Bang Theory is correct. If you go back to Unit 2, way back at the start of the class, we talked about how you can never prove a theory correct. And over time, we may discover that this picture is wrong, or woefully incomplete, or that some of our understanding is misinterpretation of the data. However, until another hypothesis comes along that can be tested, can predict what we already see, and make predictions that the Big Bang Theory cannot make, and these predictions are found to be true, until we have that scientific hypothesis, the Big Bang Theory stands as a well-tested concept of how the universe was created, how it has changed over time since then. And that's a high bar, and that's something that no other hypothesis has yet passed.